Hello everybody, Tristan here. Alright, summer is here, the uni is over, it's time to get back to my main project. So, in this video, I'm going to review all the previous prototypes that I've done for my electromagnetic AEG, and I'm going afterward to explain and review my last prototype that I think will work pretty damn well. So, first of all, let's explain the concept. The concept is quite basic. We'll just take a cylinder from a basic AEG, and our aim is to push a piston head back and forth. But instead of having a piston like regular AEGs, we will actually put some magnets, and we'll have a housing, and around this housing we'll have some coils, and these coils will just push back and forth the magnets, so they will create a motion. Anyway, so that's the main concept. Pretty basic. That's the idea is pretty basic with this technology. The only problem is to find, the coil, the right length, the right amount of turns, so that we can have the right force. So, first of all, we're going to review the previous prototypes. So here you can see, these were my two first prototypes with immobile coils around a housing made of aluminum, because aluminum is actually doesn't interfere compared to steel or iron, doesn't interfere with magnets. So what I mean by this is, look, it is not attracted by the magnets, so that's quite fine. Anyway, so the concept in these two prototypes was quite simple. A main coil around the housing that will be immobile, and then we will put some current. The magnets were supposed to go back and forth. So it was working. You can see in a video in my channel with a scar. That was where you have actually BB going through my living room. It was the system used. Main problem, it actually wasn't powerful enough for a good reason. The magnets are actually quite heavy. So you were losing a lot of power. It will take quite a lot of time and power just to move and just to give some inertia to this piston head. So that was my main problem. Quite reliable, because as you can see, these magnets in the end were just going through housing. These wires were not moving. I said this coil was immobile, so it was quite reliable. That was the main point for this, but not powerful enough. That was the main problem. So then I moved to my second prototype. So these prototypes were actually the opposite. The magnets were immobile, but you'll have a housing, so this one 3D printed, with a main coil, a piston head at the top, and the whole coil will move back and forth. And why is it actually a good idea? So this was based on the idea from the concept of the MTO. So it was a project, I don't know if you heard about it. It was a whole project who started the whole idea of magnetic rifles for airsoft. So the concept was actually created from Magneto Research. So that's the company who developed the MTO. So, well, in the end, the MTO never came out. We'll never know why. That's a big mystery. But anyway, that was the concept. It is quite efficient. Why? Because a coil, compared to magnets, is quite lightweight. So it will be very energy efficient, and power efficient. So in the end, for the same amount of power, you'll get a better efficiency, because it's lighter. So in order to get the same acceleration than the other, you'll use less time and less energy. Anyway, what is the main problem with it then? You'll say, well, let's use it. Well, you can see it right here. In the fact that you have to move this coil back and forth, you'll have actually some stress over here, and this stress will cause the wire to give up at one moment, as you can see right here. You can see the wire in the end. You know, to go back and forth here, well, your wire will just, you know, will just give up. Will just detach and will just break. So obviously, no more wires, no more energy through the coil, so your gun will not fire anymore. So I didn't really like this concept. I mean, because of this. I mean, if I want something that is works pretty well but not very reliable, I will just go for a DSG. I mean, you know, a good DSG. It's not the best solution. It won't last for ages, but you'll get you know, a very decent reactivity and stuff. Let's take for example, you know, Umbrella guns, you know, the customs from Umbrella Armory. Look at it. I mean, that's pretty enough for Airsoft. So that's it. I'm not saying they're not reliable. I'm saying with a DSG you can get something quite wow. You know, more than enough for our hobby that is Airsoft. So I just gave up. So if we take in the end the best of the two worlds, we want something more powerful, but we want something, and I mean, more powerful but more reliable. So in the end, my last prototype is this one. So how do we do in the end to really get the sweet spot? You know, this good compromise between power and reliability. Well, it's not very easy, but after calculation, we can assume something. We will start from, in the end, what we need in the output and then design the coil. Because before, I was just designing coils, changing the length of the coils. You can see the difference here. Checking if it was powerful enough or not, and then, you know, winding again. So that wasn't very time efficient, and it never quite worked out. You know, of our infinite possibilities and solutions. So this time, I just, you know, took time, just sat, take my Excel sheet and some softwares and some proper formulas, and try to do it in the end in an engineer way. I just took my output, what I need, and then designed the coil regarding to it. So, if we take, for example, Tokyo Marui stock spring, so for 300 FPS, well, after measuring, we will get 5 Newton per centimeter. That will be the stiffness of a spring, and this is what in the end the spring will actually just, you know, give to the piston. And if we take SP 110, so for, you know, 400 FPS, depends of your custom, well, you'll get 6.5, you'll need 6.5 Newton per centimeter. These are the two stiffness. We will try to be between both, because obviously, you know, on main fields for AGs, it's like 350 FPS limit. So we'll try to be between both to reach a sweet spot. Anyway, so in my calculation, I will just assume that we were using a 11.1 LiPo. And in the software, after, you know, trying layers and stuff, because in the end, we kind of, my aim was trying to fit it in the stock tube. So, no, a buffer tube, sorry. I will try to fit it in a buffer tube, but I'll talk about it later. So, I've just figured that, so 0.75 millimeters. That's actually the wire that I'm using right here. These are the ones that you can sometimes find in quite torquey motors. Anyway, so I'm just going to use this, because otherwise, if you're taking a wire that is, if you're widening with a wire that is too small, you get some, you know, joule losses. Your wire will just heat up, and well, anyway, that sounds to be the sweet spot to me after trying different diameters of, cross sections of wires. Anyway, just move on. If I'm using 11.1, with a 1 centimeter wide, so that's what you get here, for example, on a 1 centimeter wide coil, that will be, and the whole coil should fit in a buffer tube, well then you'll get 5.54 newtons. So the coil being 1 centimeter long, well, you'll get 5.54 newtons per centimeter. So if you actually check, it's indeed kind of between. You'll maybe expect 310 FPS yet, but anyway, I think that's kind of a good spot to be. So now we have actually a coil that will actually provide us enough force. If you ask, and if you want to make a DMR just for fun, for the same coil, I just tried with a 14.8 volt LiPo, and you actually reach 9.7 Newton per centimeter, and that's way beyond our SP110. So yeah, you won't even able to play with it on your field, but anyway, just to give you an idea that this technology and this coil can actually bring you somewhere quite good. So now the question is, well, it's cool, you have one coil, but I mean, well, for example, okay, with this centimeter of coil, you'll manage to bring maybe your magnet here, but how do you do here to actually bring them a little bit forward and forward? Well, that's a good question. In this case, we'll just have to check. On an M4 type barrel, your piston will actually travel 3 centimeters. That's roughly the distance that your piston will do. Because if you just check in your cylinder, here you'll have the limit, of your cylinder head. So your piston will start here, and just go back here, and then will be released. So this length right here is 3 centimeter. But if you want a full length cylinder, it will be like in the end 5 centimeters, approximately, obviously. So if you think about it, we'll just need, in the end, 3 coils, because each coil is 1 centimeter wide. So you just need 3 coils for an M4 type barrel, and you'll need 5 coils for a DMR style. So you just have to stack your coils all around the housing to kind of reach the cylinder piston ratio, so that you don't have a jowl creep in your barrel, if you follow what I mean. Anyway, so this concept should work. I mean, in order to drive the 5 coils, I will use the same H-bridge controller controlled by an Arduino. I'll just use the same one, and obviously we'll need enough of them to control the 5 coils at the same time. So from here, the paper should work, but how do you do? The main question here is, how do you do to know when you will, for example, just imagine you have your 5 coils. How do you know which one you want to power up? And then, for example, it's obvious, right? If your piston is right here, and your magnets are right here, and you want the piston to go forward, well, you just need to turn on this coil and not the coil here. It's obvious, right? Because this one is so far away, you just, lose energy to power this thing, but you won't even need it in the end. So the concept is, you will just turn this one on. You will just kind of repulse the the magnets, then you'll turn the coil that will be right here on and switch this one off. So it will move, move, and so on. But the question here is, how do you know where your coils are? When do you know the right timing? When you want to switch this one off, switch on, because it's quite obvious. If I keep this one on for the whole cycle, it's quite stupid, right? Because when my coils are going to be almost at the end, why would I bother keep this one on, right? So if you want to optimize the whole thing, we have to know exactly when and where the coils are reaching a certain point. You see what I mean? You're not going to leave this one on for the whole cycle. No, it doesn't make sense. And for example, how do you know that actually your coils are all the way up? How do you know that your cycle is done? I mean, you can put a timing. You can say, alright, I'm just going to turn this one on, switch this one on for 10 milliseconds, then switch it off. But guys, come on, it's not precise at all. It's not optimized. So maybe your battery won't last the whole day. Your battery will say, oh god. And obviously, your coils are going to warm up. Because that's the main problem with this technology, is the heat that will be produced by the coils. So how do you do this? Well, quite simple, you'll say? No. What I came up with is a very basic idea, but it's quite reliable. This is what you want here. That's the main word in this build. It's quite reliable and quite easy and cheap. So the concept here is, so I'm just going to plug it in just to show you. Just imagine that at the end of the housing, you'll get a photosensor right here. Let's just focus. A photosensor right here and an LED. Let's see the LED that is turned on. So, the main point is these are going to be in the housing and the end, just like this. And what is going to happen is quite simple. When the magnets are going to come closer and closer, the light is going to diffract on, if you can see, yeah, just like this. It's going to diffract on the back end of the magnets. And so it's going to reflect and go back to this to the photosensor. So this photosensor will actually see, because closer the magnets will be, brighter the reflection will be. It's very basic. And so this guy will actually check it, will measure it, and we will then know the exact position of the magnets. For a certain value from the sensor, we'll be able to know, okay, the magnets are, for, 1 centimeter away. So what we can do then, if we do know where the magnets are, we can then switch on and off the coils, regarding to the position. So we can optimize the whole thing. We can optimize the whole. The whole cycle and get the best power out of it. So this is it. So this sounds quite simple. I think I actually do have all the main components. What I do need to do now is to 3D print a new housing, because as you can see, I just recycled whole housing that I used for one of the first prototypes. So I just need a proper one. I will need then to wind my 5 coils on the housing. That sounds quite German when I'm saying it. And that's it. And just put at the end of a housing like one of these photosensor and one LED, and just do the program. But in the end, this is it. Quite simple. Just buy my H bridges, So to kind of to do the connection between the Arduino, that's using very low currents, and the 30 amps that will be used by the coil, from the battery to the coil, I'll just use this 8 bridge that will, as its name says, that will just do the connection between both. I'll need a couple of them, 2 of them, to actually power the 5 coils. So this is it, guys. We have something, according to the numbers, it is supposed to give enough power. Something that is supposed to be powerful enough. So that's it, guys. I'm just going to post new videos when I'm going to finish the first prototype. So anyway, take care, guys, and see you later.